developed. As per my opinion, I will try my best to cover the things because I expect the participants may have different chances or the possibilities to start their research work and to explore various opportunities. So that's why I'm covering a little bit more kind of concepts which are covering under this advanced materials. So first of all, what are meant by these advanced materials means these are very basically processed and synthesized, fabricated and manufactured, developed high performance property materials. Okay, so advanced materials means we need to process it, synthesize in the lab, then fabricate it for a particular purpose of the device development. So that is the key role which it takes place in this advanced materials. And of course, in this advanced materials, lot of things we need to develop. Basically, from this alloys, I think you can see this cursor. Okay, alloys are there, polymers are there, biopolymers are there, porous materials, particulate materials, fiber structures, composites, metamaterials, and many more. So these are few, many more are there. And as per the interest of the people's choice, they can select. And of course, here the main guiding tool is the device. Whatever the requirement of the device or requirement of the particular target objective, as per that we need to design the material. So when we are starting the designing of a material, this is a simple flow chart. We need to think in this way. So why I'm showing this one is to get who are the newly developing people in this research area of functional materials or the advanced materials. First of all, we need the design requirements. So this flow chart will give you a little bit idea. So what is the requirement that we need to identify. So then what required properties I need to probe for that, and what is the required shape I need to tune for that. Then material selection, processing method. So these are interlinked also. And then finally, anyone who is taking this material or the device, they find the cost effective. So that's why cost is playing a major role. And then finally, one of the very important concepts is whether this material which developed or the device which you design, is it economically eco-friendly or not? That means green material or not. Even government is looking for this green materials. So that green material development is one of the responsibility for any researcher. It should not leave any kind of hazardous to the environment. And then we need to meet the decision and final choice. So this is the flow diagram. After that, the concept how it starts is first of all, material we need to process it. Okay, we have so many chances to process this method of techniques for this material. So whether it is powder form, okay, polycrystalline or amorphous material, single crystalline material. So these are the processings which we need to design it. Then we need to identify the characterization. All the materials will not give the required final outcome. So we need to confirm that structure. So based on the phase, morphology, okay, size, grain size, all these things to be confirmed, then you will meet these required properties at the final. So this is the processing to the structure identification, then finally meeting your properties. So these are the various phases which you need to cross out during the research and development. And generally in this material properties identification, we go with this physical, chemical, electrical, magnetic, thermal, optical. So these are the certain material properties we need to characterize. And of course, based on your characterization techniques which are available, and you can take it from any of the standard laboratories, you can go with this kind of properties identifications. So under the physical, we need to take this boiling point, melting point, shape, structures. Okay, then chemical structures, acidic nature, composition, corrosion resistance. Then electrical properties, majorly electrical. For the sensor properties, they play a very crucial role. And of course, magnetic, thermal, optical. So once the material properties are confirmed, then we have this similar kind of properties which comes with this, just like say previous slide, chemical, dimensional properties, physical, mechanical. So a lot of mechanical properties are required. And of course, as I told in the beginning itself, based on your final requirement, you need to go for this number of characterization techniques for the properties identification. So after this advanced materials, one of the structure which comes in that one phase materials are the functional materials. Okay, these are called functional materials or smart materials. So these functional materials, they are finding nowadays lot of applications like in the biomedical areas, aerospace, optical materials, structural materials, energy technologies. So today, even in my talk also, I'm going to cover some of the major government interested as well as funding research oriented concepts also I'm dealing today. So those concepts I'm going to deal in this presentation. And recently nowadays people are working for this metal organic frameworks also. So these metal organic frameworks, they are the crystalline form of porous materials. So their porosity may be mesoporous or microporous nature. So microporous means generally they will have this uh, pore size of zero point 0.2 to 2 nanometer size, and as well as mesoporous, it will have 2 to 50 nanometer porosity size. Then we have even macroporous also, which contains around 50 to 100 nanometer size porous structure. So these porous structure materials, they find compared to the silica materials. So compared to the silica materials, they are finding around 1,000 to 10,000 meter square per gram. That area covers. Okay, compared to this geolized carbon materials. So this is one of the recent technologies which are applying for many kind of sensor developments also. And of course, from the cost point of view, if anyone would like to go for any research work, we need to find the progress of that particular area. So this particular electronics industry market, uh, the cost will, that means the CAGR, okay, so capital growth, it will go up to 7.4% growth, which is expected. So interest in this research area of electronics will boost future. And many industries are also looking for many kind of different materials for their applications. So here from onwards, I am giving the one by one sector area where you can do research work in these areas. Okay, and if any doubts are there, please raise. I will try to answer for that. So first area which is very interesting to develop the research work with this advanced materials, that is the space science and technology. Because all of you know, the space science technology, India is progressing very fastly, and we are almost reaching to the number one stage globally. So that's why this space science technology is opening a lot of opportunities. So that may be either in this satellite technology or space applications or space vehicle technologies or outreach activities, space science explorations. So this spacecraft and science of payloads, they come with this kind of different area of subject concepts. So one is you need to see the earth sciences, astronomy, so then electronic space technology applications, then your mechanical, chemical, physical, life sciences, all these combinations are necessary. Once if you are designing any material, these properties may influence at certain location. So that's why we should be a little bit careful while designing our advanced materials. So then in this space technology, we have aviation technology is also there. So this is also aviation technology which is giving the very huge opportunities. So initially I told this functional materials, they are the group of engineering materials, okay, so designed to synthesize for a specific application purpose. So you will find this chromium, titanium, aluminum, boron, iron. So this kind of combinations, metal alloys, you can take it. And in this one, you will find this gamma phase iron, which is called arsine also. So this is the face-centered cubic material, FCC structured one. So this will give a very good lightweight material as well as strength enhancement also, which is a very requirement for this development. And of course, that will be combined with this different matrix elements like nickel, cobalt, iron. So this is one of the big area people are looking either in this turbines as well as fan blades. All these materials to be developed there. So these are different types of materials which I have the exploration futurely. So they may have come from this stainless steel, and where this is applicable in this different sectors, it was written here: cobalt, chromium alloys, titanium alloys. So this is of course given in this particularly uh, biomaterial applications. Future next slides, I'm going to discuss these biomaterials. There you can see here. So coming to this advanced materials, okay. So I told you the major key roles which play there is the strength of the material versus temperature. So the strength of the material should be very high, particularly up to a high temperature. Then it will be very best material for certain applications. Okay. So you can choose either from this steel. You can see up to nearly 700, 800. Steel is better working, and below that titanium. And this is metal matrix composites. So this is also one of the very used automobile applications are there. Metal matrix composites. Titanium is there. High temperature applications, and even this polymer matrix composites (PMCs). PMCs at low temperature they give very high, strong, and lightweight compositions. But if you need the very high temperature stabilities, we need to go for this nickel-based composition. And even these oxide materials and thermal insulating layers, composites coatings are required at this CNC compositions. So this is the particularly chance for the material selection. And even this bottom one is also showing this phase diagram, the strength versus temperature, how you can select the materials. The combination of the materials were written here. So that is from this carbon fiber or glass matrix or ceramic materials. So that kind of materials you can select. So this is particularly initially I'm discussing for this space applications as well as defense applications. So after this space applications, the next choice is we can go for this defense applications. Now this ISRO as well as DRDO both are funding very hugely for their research projects. So you can choose any kind of topic from these applications from this space and defense sector. So of course the budget allocation in this defense sector is very huge. Okay, so all of you might be knowing it. Almost 13% it was highlighted in this budget. And in future the growth is very high, which is 6.2, which is approximately expected up to 28 billion crores of market in this advanced materials defense market. So that's why a lot of opportunities they are available in this defense sector. So in this defense sector, you can go for this air or naval or land, air, electronic based, missile based technologies. And in this defense applications, you have the fighter jet. Even nowadays, drone technology is also coming. And in this defense subsystems, you have the airframes, okay, propulsion techniques. Then in the components, you have the wings, turbines, these kind of even fabricating materials. This can also be taken. And if the semi-finished materials, alloys, materials like aluminum, titanium, nickel, this kind of composite materials, you can choose this material. So various applications you can find in this defense sector. And while designing this kind of materials, you will find this kind of structures. You can select the oxide materials like structure of AB2, AB1 perovskite structures, or composition materials, polymers, or in this oily materials, okay, light emitting diode material, then top down, bottom up approach. And one thing what you will find in this one is once if you want to choose the material property, so here you are seeing you designed a particular material with a particular size of the composition. But once if you want to tune the high temperature or any pressure compositions, then you have to take the coatings to the surfaces. So once the coating is taking place, then the particle size may be changed. Okay, that is influence the properties also. That's why you have to find out at what size, particle size, as well as this specific surface areas, they will tune your material properties. So that is a major key role which plays in this properties final action. So then after that, of course, recently materials research is very vast area, and of course it takes a lot of time to design a material. But uh, who are interested in this design concepts, okay, that means finding with this simulation technique, that is giving the one of the best opportunity. So initially you can seek this kind of softwares which are available. So with a big database, and then you have to do your algorithm there. Then finally you have to come with this modeling of the materials. Okay, so these modelings are nowadays available, and who are interested they can take up this choice also. And of course these modeling techniques they take the initially from this atomic scale tuning, like DFT theory. Okay, so from this DFT theory, they can go for this Monte Carlo approximations, then calculated phase approximation dynamics, cal HAD, then it is FEM. So surface structure changes you can do this with this FEM. So all these compositions you can find out in this simulation modeling, and then finally you can confirm what type of properties I need to tune for the material. So just in this modeling, just I'm giving one example how this will reduce the time as well as the laboratory work experiences are. So this is one of the paper they have done this kind of simulation method. So generally what people are claiming is for aerospace industry. So to design a device, it takes 18 months. Okay, so 18 months to design a material and 10 years to design an ideal material. Okay, to devise a design of this 18 months material, 10 years effort is required to take this material properties to it. So which is very huge timeline. But whereas if you apply this kind of simulation techniques, your time will be very much compressed and you will get with a required properties which are necessary. So this simulation with theoretical physics modelings nowadays very huge opportunities are also available there. So after this space technology, now just I am entering into the next one. Of course, it is the nanostructured materials. I think all of you are having good idea about the nanostructured materials. So briefly, what are the nanostructured materials means? The materials which are having the size 1 to 100 nanometers in any dimension. So this is one of the very requirement. Dimension is required. Okay. So based on this dimension, we have different types of materials which we can explain. Zero dimension or one dimension, two dimension, three dimension. So zero dimension, of course, it is quantum dot structures. Optically, they are very active materials. We have different optical tuning structures are available in this zero dimension. Semiconducting materials, you can show it. And of course, fluorine also coming here. And in this is one dimensional, which are your nanorod structures. Then two dimensional, thin film structures. Three dimensional, we have the polycrystalline form liposomes, dendrimer structures. So this synthesis of nanostructured materials, of course, this is also I think all of you know very well. We have the two methods, top-down approach, bottom-up approach. Based on your laboratory requirements, you can select any of the method which is available to your comfort. So there are four different methods which are available for this synthesis of nanostructured materials. You may select either physical, chemical, biological, hybrid methods. So nowadays, even bacteria phases, they are generating these hybrid structures. And biological, uh, you can find it with microorganisms. Nanoparticles can be synthesized, and chemical and physical. Ball milling, melt mixing, and this is physical vapor deposition. And of course, chemical vapor deposition comes in this hybrid method. So this is the thing. We may have this one-dimensional graphene, which is generated from this fluorine structures. So allotropic form of carbon, so graphene and carbon nanotube fluorine. So in this one-dimensional, you will find this CNT and this graphene, which is rolled there. And in two-dimensional, we have the fluorine structure, which is CNT. Okay, so then film structure we will find it. then graphene armor, two-dimensional film we can form, and in three-dimensional we will get this CNT and graphene structures. So this kind of nanomaterials nowadays finding many applications. Just I'm going to explain one by one. Either in this water sensors or electrocatalytic applications, okay, spacecraft applications, sulfur capacitors, solar cells, then biosensors, volatile organic compound detections, humidity detection, soil testing. So these are various applications. And of course, this is again one of the bottleneck approaches which are obtained from this nanostructure materials. So this is the bottleneck nanomaterial based solutions for this propulsion thrusters. So this is one of the paper which is published in this paper. So they explain how this cold cathodes and as well as magnetic system tuning they can be improved with this nanophase structures. So this is the good explanation you will find out in this particular article. And of course, carbon materials as well as this fullerene carbon nanotubes, we are finding very huge applications in composite material development. So this is the three-dimensional one, which is graphite structure, and this is one-dimensional carbon nanotubes, which are rolled this one, this honeycomb structure, and this is the fullerene structure. So, and of course, this fullerene structure C60 that contains this surface of nearly with the 20 hexagons and the 12 pentagons. So this is the uh, CNT and graphene structure which you will find with this SEM scanning electron microscope. So this is the single walled and bottom one is multi-walled carbon nanotubes. And this graphene you will find in this RF radio frequency applications for the space. And this CNTs they will find the digital applications uh, based on the properties available. Of course, this is the graphene structure. I think again this is one of the important for getting the particular property. Uh, these are having three different structures which are zigzag, chiral, armchair. Okay, so in zigzag theta is equal to 0. That means this theta, which is the chiral vector, which is having the value of theta value here. So theoretically, you can find the theta value as well as the diameter of the tube with this chiral vector. So the chiral vector CH is equal to n times of A1 and n times of A2 vectors. They are joined, and this unit lattice size vectors they will give this value of diameter of tube. Then you will find this chiral and theta value. So for this theta is between 0 to 30 and exactly 30 degrees. They give the armchair. That means the tube end with it will show like armchair. So this spiral vector, it is helix-like structures. Okay, so this is zigzag. You will find a zigzag-like structure here. So these are the three different types of carbon nanotubes based on this spiral vector. And of course, this is the different methods for this synthesis of carbon nanotubes, like the regulation, arc research, chemical vapor deposition. So after this graphene and space applications, then next time coming to this another very important one is called piezoelectric materials. Okay, these are functional materials. So again, this is finding very huge applications in this functional materials. So first of all, what are these functional materials means? So they do a specific purpose for your properties identification. And this functional materials, one class is your piezoelectric material. Okay. So what is this piezoelectric, ferroelectric, and of course pyroelectric materials? They come from this particular class of crystal structures. So total from this symmetric class of the crystals, we have 32 symmetric classes. Out of this 32, we have the 11 centrosymmetric and 21 non-centrosymmetric. Out of this 21, 20 will show this piezoelectric. Okay. So what are piezoelectric means? They are particularly a non-centrosymmetric materials. Piezoelectric materials means non-centrosymmetric materials. Out of this 20, 10 will show a polar axis. They are called pyroelectric, and 11 will show non-pyroelectric. So leaving aside this 11 non-pyroelectric. So these pyroelectric materials they come under again with these polar structures which are ferroelectric materials. So what are ferroelectric materials means? Which exhibit spontaneous polarization even in the absence of external electrical field. Okay, so this is the definition of the ferroelectric materials. Ferroelectric materials means they show a spontaneous polarization even in the absence of external polarization. So this is how this non-centrosymmetric. Just now here I told you what are the piezoelectric means. They show the non-centrosymmetric structure. Okay, what are this non-centrosymmetric structure means? Once if you apply any pressure on the material, here it was shown. Okay, so there is no stress is applied. Then it is in the centrosymmetric structures. Once if stress is applied, then it will show a potential difference is developed, as well as vice versa. That means if I apply a potential difference, then you will find the stress or strain will be developed in this. So mechanical to electrical, electrical to mechanical, transducer type of materials, these are. So here you can clearly see this is the centrosymmetric, non-centrosymmetric conversion. Right? And of course, best example is silica. So SiO2. So this silica material, this is a piezoelectric but not a ferroelectric material. So this is the structure how it is showing your silica atoms as well as oxygen atoms. So they are under this application of tension. Here the positive is developed and negative is here. But it is compressed opposite direction, then your charge is also changing. So direct piezoelectric and converse piezoelectric structures we will find. So what is the relation between this piezoelectric, pyroelectric, ferroelectric materials means? Piezoelectric materials are the big set of materials. The silica will come here. But certain materials, as earlier in the graph you've shown there, 11 they will show these pyroelectric structures. Pyroelectric means with the temperature polarization will change. And then ferroelectric material. Okay? So any material which is a ferroelectric, automatically it will become a pyroelectric and as well as piezoelectric also. But any material which is piezoelectric, they may not be ferroelectric. Best example is silica. So the characteristics for this ferroelectric materials, they show this uh, ferroelectric phase transformation as well as your hysteresis loop also. So that is a very much requirement for this ferroelectric materials. So these are different kinds of piezoelectric materials which are developed by different research groups. Like if you are interested, you can select any of the material and you can develop a piezoelectric material. So they may be under ceramic materials, polymers, composites, and biomaterials, natural piezoelectric materials also there. So you can find different types of materials which you can select from this chapter of the piezoelectric materials. And of course, again, this is the types of piezoelectric materials. Okay, we have even natural piezoelectric materials also. But now, for your materials which are synthesized in the lab, for your particular applications, you have to do the composite materials development using this combination of materials. Either you may take polymer into ceramic or your lead-free material into polymer. With that combination, you can design and you can develop the material. And in these synthetic materials, people are nowadays working even with this gallium orthophosphate. So particularly this hysteresis loop, that is one of the very much characteristic for this ferroelectric material. Once if you design a material in the lab, and if you want to confirm whether it is a ferroelectric material or not, you have to do the Steyr tower circuit, which is giving you a ferroelectric nature. So if it is dielectric nature, you will find this linear nature. But if it is increasing the dielectric linearity, non-linearity, of course, ferroelectric materials, they show the non-linearity. So your non-linearity will enhance. Okay? And of course, the increase of domain size also. But at a particular domain size, ferroelectric materials, they show this relaxer properties also. Okay? So relaxer ferroelectrics and ferroelectrics. These are the two different concepts. So this is again the same kind of ferroelectric nature which is changing. And of course, this is a polarization change with temperature. Okay, so from this low temperature to high temperature, if you increase, the polarization is going to increase. That means there is a phase transition. So this is the particular slide which is explaining this ferroelectric characteristic, which is called Curie temperature. So below the Curie temperature, we call that as a ferroelectric nature, and above the Curie temperature (Tc), we call that as paraelectric. So the transition takes place. It is like a normal distribution. So from ferroelectric to paraelectric, it will change. So the temperature where the transition takes place, that is called Curie temperature. So this is a relation between Curie temperature as well as permittivity epsilon. So this is the example for this barium titanate. Okay, so barium titanate basically will show four different phase variations, right from this rhombohedral, orthorhombic, tetragonal to cubic. So cubic structure, it is a symmetric structure where you don't find this ferroelectric nature. That means it is a symmetric structure. But all these three methods, okay, right from this low temperature is 90 Kelvin, 90 to 5, then 5 to 120. So all these three, they show non-centrosymmetry, which is rhombohedral, orthorhombic, tetragonal phase variations. So this is the change of barium titanate. With the temperature, the phase is going to change, and finally above 120, it attains symmetric nature where it is not a ferroelectric, that is paraelectric nature. And of course, nowadays people are working with this multiferrite materials also. This is particularly for this memory materials, MEA RAMs, okay, random access memory materials. People are working even in this Wintronics also. Multiferrite materials are highly used. So this multiferrite materials, bismuth ferrite material, which is having this Neal temperature around 370, and which is again this bismuth ferrite material. They show this Curie temperature, ferroelectric temperature around 830. So this is one of the very hugely studied material for this multiferrite materials. And of course, when you are designing this multiferrite ferroelectric materials, you have to choose various properties. Here, for example, I given here oxygen vacancy adjustments. Okay, so this oxygen vacancy arrangements, if you can choose this, your magneto-electrocoupling factors they will change. Okay. So even in this ferroelectric materials also, mechanical coupling factors, D33 coefficient, K11 factor. So those kind of coefficient coupling factors, you have to get it very high values. So for that one, you have to choose the different structures. So this is the ferroelectric, this is the relaxer ferroelectric. I told you, ferroelectric materials, they come with this memory applications, sensor applications, actuator applications, energy generators. But whereas this relaxer ferroelectrics, they have different applications like capacitors, flexible displays, and then electrocaloric devices. That kind of applications you will find with this relaxer. And of course, this is one of my even my personal interest area. Nowadays, people are mixing the composite properties of the materials. So one side we have the semiconductor, and another one is piezoelectric material, and another one is photo excitation. So why can't we mix all these combinations? Then we can get a complex structure of materials. Okay. So if you combine the semiconductor with piezoelectric, the new area which is emerging as piezotronics, that is one area. And if you combine this photo excitation with piezoelectrics, we have the piezophotonics, and this semiconductor with photo excitation, we have the optoelectronic materials. So these composite structures, they find very different applications in different engineering sectors. And of course, this is finding very huge development in different areas of technologies nowadays. Because of this device miniaturization, we need this kind of complex structures to be developed. And of course, piezotronics. Okay, here I told you piezotronics. Piezotronics means we can combine this combination of semiconductor with piezoelectric. So this piezotronics, which is developed in this 2006 by Wang Group, so where you can combine the semiconductor structure with this piezoelectric material. So when you combine this material, this is the explanation. Okay, how this can work out. You can see here, this is one of the best example or the suitable for this explanation for this interaction between the piezoelectric and metal structures. So you combine the metal with a piezoelectric material. Okay, So this is semiconducting piezo material, which is zinc oxide. So only studies are majorly reported for the zinc only till now, and still further more materials are nowadays people are exploring. So here what you will find is you apply for this piezoelectric material, strain is applied. Here the charge is developed at this metal and the piezoelectric semiconducting interface, okay, which is junction barrier location. And of course the stress is applied here. So here the charge is replaced. Okay, here it is negative, here it is positive. And based on this positive negative, whatever the electron densities from the metal, they tune this junction barrier. Okay, that means Schottky barrier effects. They will tune here. The height will change. So that will create the transition from these electrons from one location to another location and giving this. And of course, this kind of similar phenomena you will find even in the field effect transistor also. So FET we have three terminals, but with this particular piezophonic structures, you will find only two terminal structures. You will tune the material properties. That is the one of the beautiful of this piezophonic structures. And once you can find this C and D, here what happens is here the P-type material, N-type material. Top A and B it was explained with this metal, but C and D we have the choice of P-type material, N-type material. They can join with this visual materials. Okay. So still more complex structures we will identify. So here what is the thumb rule is, here I explained it, this thumb rule. So once this negative is coming, okay, once because of this application of strain and stress there. So the negative is coming, then electrons will repel, your barrier will decrease there. And if it is positive is coming, electrons will attract and the barrier will be decreasing. Okay, that is the application what you will find with this. So generally the negative piezoelectric polarization charges induced near the barrier. So this is the negative. Okay, this is the negative, and that will repel the electrons. Here it is repelling the electrons, where you will find this barrier height will be increasing, and here this Schottky barrier height will be decreasing. And positive piezoelectric polarization, this attracts the electrons towards the interface. So based on that, you can tune the properties, and you will find the different piezoelectronic applications. So these are the another next application. I'm coming to this medical device applications after the space and the piezoelectronic, okay, auto mechatronic applications. Now this is the applications with this medical devices. You will combine the different properties and you will get these materials for this different implantable materials. So this is again one of the biggest area for the research topic. So nowadays people are requiring either in this eye implantation, shoulder implantation, hip implantation, so different medical dental implantations, heart implantation. So and India, there is a huge scope. Uh, Even the government of India is encouraging for this self-sustainability for this biomedical devices. So those who are interested, they can take up these biomaterials as a research work. So what is the requirement for this biomaterials means? First of all, their compatibility, because they are coming into the body cells contact, so they should be accept to the body. That means compatibility. Then whatever the different material properties, they should be tuned with that mechanical properties. Like if it is a bone or hip type material, or if it is a stunt material, heart stunt material, based on that location, you have to tune the mechanical properties, then corrosion properties. Because it is within the body, your blood, bones, flesh, everything will have their own effect on the material. So that's why the corrosion properties to be confirmed there. So these are the different requirements for this biomaterials development. So till now, people are working on different types of bio implantable materials. Okay, so they are magnesium based, or titanium based, or the tantalum based, cobalt, stainless steel based. And here it was explained what kind of applications they will identify. So different implantable materials at the body locations you will find. Even the materials are given here. Okay, titanium, aluminum, vanadium, so cobalt, chromium combination, and even this titanium based chromium materials, three-dimensional materials, magnesium based. And the future is in this bioimplantable materials. We are going to see shortly this wearable sensors. Okay, so nowadays the calories which we are burning, as well as what is the BP, what is the heart rate, everything we are finding it with this bioelectronic medical devices. That is our future technology, which is shortly it is going to be explored. And this is one more interesting area using this ultrasonic. Okay, nowadays people who are affected unfortunately with the cancer, so they are going for this chemotherapy. Now the future with this functional materials, we may face this very easy way with ultrasonic sounds. So this is research area which is exploring with this sonodynamics therapy, SDT. Sonodynamic therapy means the cancer cell, it will be given with this ultrasounds, and they will repair that cell. Okay, so that the cancer cells they may not explore to the further locations, and it will heal there itself. And the uh, damage to the further cells will also be very much minimized. Otherwise, the chemotherapy that causes very huge damage to the total entire body structures. So after that medical, the another big area, even the government is telling is hydrogen storage awareness, okay, and as well as solar energy. So this is advanced materials which are very much required in this photocatalysis. So what is this photocatalysis means? This is the rate of photoreaction or chemical reaction that involves absorption of light, one or more reaction species. So majorly in this, by adding the substance catalyst, okay, so with the chemical reactions without being consumed. This is the photocatalysis, where you have to find this oxidation reduction reactions takes place in this photocatalysis. So this photocatalysis again, very huge area finding applications either in this pathogens killing. Okay, so if any molds or any bacteria or virus is there, recently in the COVID time, people applied this photocatalytic materials as a surface coatings for the killing of the virus also. This is one good area to develop, like silver nanoparticles, which are finding this kind of applications there. And of course, even in the food applications, we find this photocatalysis applications. Titanium dioxide, it is one of the best photocatalytic materials, which is highly studied in this photocatalysis sector. And of course, if you find this photocatalysis, this is a replica of your natural photosynthesis structures. Okay, so this is the leaf which is giving your oxygen at the output. So similar way, if you find this photocatalysis, you will find this oxidation as well as reduction reaction which takes place. Here it was explained. So once this material is exposed with this particular energy of the light photon, then electron will jump from this valence band to the conduction band and creates one hole here. So this is a reaction takes place, and this hole and electron which are generated in this conduction band, valence band, they react with the surrounding oxygen as well as atmospheric water vapors. Okay, so here this reaction is explained. So this electron which is interacting with this oxygen there, and it is becoming the oxide radical. Okay, so it is a superoxide radical, O minus, O2 minus, and of course this H2O. So that is taking this whole, and it is becoming hydroxyl radical. So this superoxide radical and this hydroxyl radical, they will give the requiredness for your controlling your dye structures. That means water purification as well as killing of the pathogens. So because of this oxide radicals, they damage the DNA of the pathogens. So just now I'm going to explain that. Yeah. So this is the explanation how they damage the DNA of this pathogen with this titanium dioxide. Okay, so this is the oxide radicals. They interact with the DNA and they damage. And even nowadays, at our lab also, we are trying it for the packaging materials. If any food is spoiling with these microbials, then it will be killed and the shelf life can be enhanced. So this is one of the great area of research work. And even the solid municipal waste, whatever the effluents which are coming from the industries, they can also be treated. And this is already practiced worldwide globally. globally, many companies are working to control the effluent discharges to enhance this oxygen layer and as well as controlling the chemical effluents in the materials. So after that photocatalytic mechanism, this is the hydrogen generation. So this hydrogen generation nowadays, lot of funding is available. You may take up this work also for this hydrogen development using the photocatalysis. So in this one also, a metal-based photocatalysis you can take up, or carbon-based photocatalysis you can take up, and from this water, by splitting this, you can get this hydrogen. So this is the mechanism how that takes place. So uh, just now recently I saw one of the very interesting. Along with this water, nowadays people are using this. That means this is a very recent area reported the waste material. Okay, so whatever the waste is there, like agricultural, forest, or domestic waste, they are also using for this development of hydrogen using this solar light. So this is one of the interesting area. That's why I'm showing here. So you can find the applications using this. Of course, it is a dual application. We get the green energy and by minimizing the solid municipal waste. So both will be applicable in this waste technology as well as energy consumption. So after this energy, hydrogen, okay, so this is and again one more very important, which is agriculture sector. So we find lot of applications in the agriculture sector. So this is the nano pesticides and fertilizers are available. Um, I think you might be hearing in this particular thing. Government of India they released the urea. Just I am showing it. Nano urea. This is worldwide. India developed it first, and our honorable Prime Minister uh, released it in 2021 for this farmers. And you can find the very huge difference with this nano urea as well as regular what is farmers are using normal urea, okay, which is the fertilizer. So this 50 kgs of bag, which is equivalent to 500 ml of the nano urea. So this is a huge difference which is bringing, and because of this nano urea, globally, lot of greenhouse gases which are delivering with this urea delivery, they will be reducing, and even the transportation. So very huge transportation cost is involved in this transporting of that means logistics, 50 kgs of bags as well as 500 ml bottle transportation, and of course the shelf life. So nano urea it should not be hygroscopic. Then this 500 ml bottle, there is no problem in this storage method. So this is the patent which is given to the IFCO, nano DAP and nano urea, and the consumption is also only 2 to 4 ml is enough for this crop. You can see here the cost effective. Okay, liquid nano urea this is only 240 rupees, whereas nano urea bag which is 3,500 to 4,000 rupees. So this is a huge benefit to the farmers expenditures also. So this is the future technology which it is expected. That means it is a customized dimensional development of fertilizers for the agriculture. So future we will find out this kind of technology also. That means not the entire crop, but only customized development of the fertilizers as well as pesticides. It will be identified. This is the development technology which is reported by the Egypt people. So after that, future you may find the combination of these fertilizers as well as pesticides also. This is encapsulated material, not only single material like urea where you will find out, but here the combination of materials like magnesium, calcium, micronutrients they are combined and they are proposed for the material which is dual stimuli sensitive materials to the crops. And now after this agriculture, this is the another technology which is coming with this food technology. So this is our institute mandate also. Lot of industrial applications and there are lot of problems are there in this food sector. So you will find out in this packaging, okay, food safety. And of course, in food functionality, you have to design new products, then food preservation. So all these locations, you will find these applications of functional foods as well as materials. So this is in the food sector, one of the biggest area. Of course, even in the right from the beginning, I told the aviation, space technology, everywhere sensors. So this is the one of the biggest area. And sensors, it is a block diagram. So first of all, you will find one analyte. Then it will be finding a biological interaction with a enzyme. That means it is a selective reagent which is binding there and giving the transducing material, either optical, electrical, electrochemical detection, then output. We have to find out at the output. The simple example is glucose sensor. So people who are diabetic, they regularly use the glucometer for the detection of blood glucose levels. That is amperometric electrochemical sensor. That is, and even in the COVID also, people use the rapid detection testing kit. That is the biosensor development. And of course, biosensors, it is having a huge area for applications. Just now I told this block diagram of the sensor. You may find this analyte bioreceptor, either maybe antibody, enzyme. The major will be identifying this kind of bioreceptor and the method of electrochemical or optical, how the transducer is taking place. You have to play in between these. Then, what is the advantage of this one means the conventional methods like chromatography or HPLC, LCMS, these are having crores of rupees of expenditure, but the sensor's cost is very low and they are on-site detection. You'll find at the on-site location. And of course, in the sensor, we have the optical, mechanical, chemical, biological nanosensors also. This is a colorimetric sensor. And nowadays, the sensors technology, they are coming with this 3D technologies also. So this is one of the big area going to develop. So this is the on-site detection for this plant crop mechanism. And of course, future again we are going to find out. Already it was coming into the market. So whatever the pesticide residues or antibiotic residues which are existing there, we can find out with this Android. So nowadays mobile is becoming your lab detection technique. Like that is the future technology with IoT development. So you can find this horticulture, dairy products, whatever the quality or the safety of the products also. And this is the typical structure of electrochemical sensor. So you will find here one working electrode where your analyte will be deposited. Just now I told you either enzyme or nanoparticles, whatever it is, you have to deposit here. And this is the counter electrode and this is the reference electrode. So three electrode system this is. So this three electrode system you can design at your lab by either paper or flexible substrate or any quartz substrate. So this is a simple mechanism how you can design that substrates. So here your analyte is there and you will find this electrochemical, okay, oxidation reduction peaks will come like this. And this is the one of the IIT Bombay's initiation. Okay, they've given this soil sense technology for the farmers. This is again your day-to-day consumption food, how that will be adulteration. This is rhodamine B. Rhodamine B is one of the adulteration with chili powder. This is carcinogenic, so that can be detected. And this is again mycotoxins, aflatoxin B1. This we did in our lab also. So aflatoxins are type 1 carcinogenic. Any food which is we are consuming or exporting, this is mandatory to test and confirm. That means the standard agency like FSSA, they have to give the confirmation. So this is our published paper on this aflatoxin detection. So we use this metal oxide clay composite for this aflatoxin detection. And this is MIPs, molecular imprinted polymers. And this is again either phenols, volatile organic compounds that can be detected with the sensors. Yeah. So this is almost coming to the conclusion part. Like we have this food packaging. Again, this is big area because whatever the food we are purchasing, that is coming with the packaging, and simply we are taking the packaging out and we are throwing it into the garbage, and that is causing very huge uh, solid municipal waste. So that's why nowadays people are looking for this active packaging materials where your biotechnology as well as shelf life enhancement both can be done there. So these are the biopolymers which we can develop for this bio packaging materials, which are environmental friendly packaging materials. Like so that may be either from this cytosol, gelatin, cellulose type of materials we can develop. So this is the trends which are observed with the cellulose because nowadays everyone is confirming from this plastic to jute. Okay, so we know what are the problems with the mica or the plastic. Even government also banned this. So now the cellulose is alternative, and you can find from 2015 to 22 very rapid growth of the cellulose technology development. So this is one of the big area anyone can take up there. So in future, this sensors technology it will be coming combination with this IoT techniques. Okay, this is the one of the document coming with this UNDP, which is located in the Singapore. So they are finding this all the farmers data that will be data generated, and it is IoT technology was connected there, and the farmers will be advised. So this is the where materials can be very crucial role they are playing there. For taking this camera drone technologies or as well as thermal cameras or hyperspectral cameras. To develop all this, we need a particular type of OLED video which is with quantum dot structures we can develop there. And this is the future technology which is smart farming. People nowadays confirming for the smart farming. Even the ICR, Indian Council for Agriculture Research, they are promoting this smart farming as well as precision farming. These two are the very important concepts. So I think I'm concluding here. So thank you very much for this. If any doubts are there, please rise.
If you have any queries or any question, please ask.
Sir, can you prepare nano fertilizer or insecticides for this insecticide by using some techniques or that plants are there?
Yes, already these biopesticides, biofertilizers, they are available, and even here I showed it because
Which we
of the
are
time.
nanometers are used for that?
Yeah, yeah, yes, yes. Just I'm going to show it because of the time constraint. I haven't gone through. Uh,
No, sir, we have
actually,
time. No problem, sir.
okay. So I thought it is 1 hour and you have validity function.
No, no,
That's
sir.
why.
No, sir. No, sir.
Okay. So here you can find it here. Very different types of nanostructured materials like iron, zinc, cerium, okay, single wall carbon nanotubes, multi wall carbon nanotubes. They are implantable to this plant. That means how you can give to the plant is two methods. One is either by giving through the irrigation system, whatever the water you are giving, or you can give it through the foliar mechanism. So this is the sprinkling type. So both we can give these nanostructured materials, and of course
Yeah.
the plant will contain this xylem, phloem. So they will go through these roots or the cells of the composition. Then it is the root structure of the this plant. Okay, right from this hair, okay, root hair inside to this phloem. So this is how the nanoparticles they will go there and they will interact and they give these pesticides there. So this is the nano urea, and of course after this I showed this pesticides also. This
Yep.
is the nano pesticides.
Yeah.
These are the different nano pesticide structures. And even just for your information, this month 23rd, one of the professor from USA, he is coming to our campus, and he is one of the expert in this nano analysis for the agriculture systems. His name is Jason White. You may search it.
Sir, I am interested in
Jason White.
that. For example, the Datura plant is there. These are active insecticide or
Mhm.
poisonous plant, and they can. I
Okay.
think that there, if they are using some nanomaterials
Yeah,
with that,
you
uh, the insecticide are
you
developed.
can explore. You can explore.
Yeah.
That will be very huge benefit to the farmers
Mhm.
because the surface to volume ratio, the properties will change. here just now I told you this urea points because surface to volume ratio, and where you will find that below 50 nanometer size. So that's why whatever your interest for the pesticides, you can
Yeah.
study and you can do the lab analysis.
Yes. Thank you, sir. Very good
Okay, sir.
information.
Thank you. Thank you. Thank you. Good.
Yes, any other question? Yes, any other question?
If any questions are there, you may interact. At the end of this slide, I given my email ID also. Otherwise, you may search it in my NIFTEM website. So you may contact me, and we are ready to do any kind of support from the ministry side as well as from our lab side. So then finally, I'm giving my heartfelt thanks to the organizers for giving me this opportunity. So thanks to your campus as well as the department. Thank you very much, madam.
Thank you, sir. Okay. Thank you, sir, for giving informative session very nicely and many advanced materials you covered in your talk, especially nano urea, nanocellulose, many more. Okay. Before moving towards concluding remarks, I request all the participants to share their views. Yes, anyone? I request participants to share their views regarding this STTP.
Hello, good afternoon, madam. Our STP
Good
are
afternoon,
very
sir.
good informative lectures are organized, and we are observed that from 2 to 3 years, there are the new budding scientists are there. For example, my friends Santosh Uke and other scientists also there to give the very nice information regarding the same type analysis. So it is very and budding scientists are very informative. Your FDF course. So thank you, madam, for organization and we are as a participation for that activity.
Yes, any other? I request all the participants, please switch on your camera for the photo or group photo. Please, I request all, please switch on your camera. Please switch on your camera for the photo. Okay. India is India is among the countries that have the highest number of educational institutions and highest number of teachers and faculty members. Certainly, this fact itself boosts the importance of events like STTP, short-term training program. Through such program, faculty get maximum learning benefits. Day by day, new things are added in our subject, and as a faculty, it is mandatory to update the knowledge. Learning to teach is a lifelong process involving continuous improvement. We have to adapt changes, whatever takes place in our subject. When the faculties are ready with updated knowledge, they can make their students ready. So for that, such type of programs are required. In such programs, we can learn through the experts from industry as well as from the institute. In this 5-day IST approved STTP topic, recent development in advanced material, we learned lots of from our experts. I express my sincere thanks to all the resource person. First, Dr. Bhaskar Sathe from Dr. Babasaheb Ambedkar Marathwada University, Chhatrapati Sambhajinagar. Dr. Atish Daryapurkar from IIIT Nagpur. Dr. Darshan Habare from Amity University, Mumbai. Dr. Ramesh Kamble from Government College of Engineering, Jargaon. Dr. Ashok Humbe, Dr. Babasaheb Ambedkar Marathwada University, Sub Campus, Dharashiv. Dr. PM Shirge from IIT Indore, Dr. Narayan Karmakar from Dr. DJ Sangvi College of Engineering, Mumbai, Dr. Santosh Uke from JD Patil Sangrotkar Mahavidyalay, Daryapur, Amravati, Dr. Tejo Kalyani ma'am from Lakshmi Narayan Innovation Technical University, Nagpur, and Dr. P. Murli Krishna from NIFTEM, Kundii, Government of India. So we are very much thankful to resource person, the way in which they explain their topic excellently. Thank you so much for conducting a session very nicely and effectively. I'm also thanks to all the participants for listening all this session patiently and make this STTP successful. I also extend our thanks to Honorable Kalyan Rao Jadhav, President of KJEI, Major General Samir Kalla, Executive Director, and Dr. Suhas Khoth, Principal, KJ College of Engineering and Management Research, Pune, for their guidance and support. Last but not the least, I'm very much thankful to our coordinators of STTP, Dr. Vivek Korde, Dr. Hema Kori, and Professor Mahendra Pansare, and also our organizing committee members, Professor Sandeep Sahane, Professor Asha Jadhav, Dr. G.S. Solanke, Professor Seham Khalil, Professor V.S. Dikshit, Professor Nilesh Sarunke, and Mr. Ganesh Kumbar for their contribution to make this STTP successful. Thank you very much. So this is all from my side. I request Dr. Vivek Korde to conclude the session. Over to you, sir.